All right. For today and for this week, we're going to be talking about inverse functions, specifically inverse trig functions. Yeah. So let's first. I want to describe what an inverse function is and how it fits in. If you take in college algebra right now, you've already heard something about inverse functions. I want to describe them for those that haven't, and then describe how they specifically fit in with trig ratios. So first thing to note, the definition of an inverse function. Before I can talk about inverse, it's important to recognize the actual definition of a function itself. So I'm going to go to back to the very basics, like pre-algebra style. A function is designed to do one thing. It can be really complicated how it does it, but it's really designed to do one very basic set of instructions. It takes an input value, which we typically call x, and gives an output value, which we typically call y. It is not always this case. Sometimes your input is a z. Sometimes your input is a t. Sometimes your input is whatever the heck you want to use. But it takes an input and makes an output. No matter what thing in algebra you look at, or trig, or calculus, or any math class, a function takes an input and creates an output. Now, we typically notate this with the following notation. F standing for function. What goes inside the function, our typical x value, is called the input. Or in science class, you would call it the independent variable. It then leads to an output, or y value. So again, the input is what you plug in, the output is what you get out. An inverse function is designed with this system in mind. Now, you may have seen this button in the calculator. If it's been a little while since you took an algebra class. F inverse. This is not f to the negative first power, it is f inverse. F inverse is designed specifically to do the opposite order of steps. It takes whatever output you gave and will tell you what the input was. In many practical applications, we don't always know the input. We don't always know what it started with, but we can measure through physics what the output was. So an inverse is designed to work backwards. If you know the results, you can plug the results in to find where you started. A lot of applications use this. Weather prediction algorithms use this a lot. What they do is they look at it and say, hey, we know the current temperature, so let's find a formula that got us there. We know the current air pressure, let's find a formula that gets us there. It's a constant thing in a lot of real applications. So again, it's designed to take the opposite order of steps. To put this very simply, let's look at a simple algebra function. Something like a quadratic. X squared minus 3. This is a function. It's designed to take the input x, plug it into the function, and get an output. In this case, let's look at a very simple one, f of 4. What that says is take 4 and plug it into the function and find the output. So when I take 4, I would square that 4, and then subtract 3 from that 4. So in this case, f of 4, so the input of 4 would be 4 squared minus 3, or 16 minus 3, which is, of course, 9. So for this function, x squared minus 3, the input would be 4, the output would be 9. The inverse of that function would have to do the opposite, meaning it would have to be a function where I input in 9 and get out 4. It does the exact opposite steps. Now, in algebra, you'll learn that there's a way to find inverse functions through direct substitution and solving. In trig, we don't have to do that. Trig defines its own inverses very specifically by the function. You gonna raise your hand, Ryan?
Yeah, how'd you get 16 minus 3?
Because Douglas can't do math. It's Tuesday, coming from Slack. I'll say that same thing on Wednesday, I promise. All right. Thank you for calling me on that. That was going to be really weird later. All right.
I know. I didn't even realize.
Brian, I'm going to throw a bonus point your way someday. Thank you for calling me out. I'm tired of
Either.
people just being like,
Okay, cool.
you made a mistake, I don't want to tell you. No, tell me. I'm stupid if I don't do it.
I didn't notice either, like, I was fine with 9.
Why?
We're just rolling. Alright. At lunch. We'll talk some more about the inverse when we get back. Okay, so as mentioned before we went on break, the idea of input versus output for the function and for the inverse. So for the function, you plug in the input, you get out the output. The inverse should have the opposite effect, where whatever value you would have gotten as an output, you instead plug in, and it will tell you what the input should have been. It's good to think of it in that term, that what you're plugging in should be an output, so what you're getting out should be the original input. Now in Trig, in purple up here, we have our original basic function sine. Okay? Sine we typically know as opposite over hypotenuse. But what's important to note about this is a function where what we're doing is we're plugging in an angle and getting out some kind of ratio or fraction. That's the classic trig problem. You plug in an angle, you get out the fraction or ratio. But what the inverse should be to do the exact opposite effect. So rather than plugging in the angle is what you get out of it. Rather than finding out the ratio is what you have to plug into it. So the inverse functions of these particular calculators and for these trig problems can always have the inverse effect. So where we normally plug in the angle, get out the ratio, now we have to plug in the ratio to find out what the angle used to be. So, depending on the calculator you use, and this is why I asked you to bring those out, there are 3 versions you might see depending on the calculator. Do not use the power command for this. There should be a specifically designed button for this. Now, it may be hidden somewhere, but it should be there. There are 3 versions. The first version is the most common one. It is sine inverse, or sine to the -1. That is not a negative first power. It is not a power at all. It is an inverse command. So this tells you this is the inverse of the sine function. So again, this inverse will plug in the ratio and tell you what the angle is. Alternatively, some calculators and some computer programs will use arcsine. If you use Google for any math, the most common one is arcsine. And then asine is your next most common. Those 3 are the most used ones out of all of them. So, this is my calculator. Beautiful, fancy, I know. So, on this one, as is with most calculators, your inverses are typically shift commands or second commands of the originals. So for my calculator, if I want to do the opposite of sine inverse, I hit second sine. If I want to do the opposite of cosine, second cosine. Same basic thing, every single time. You'll notice that we're only sticking with the big 3 because the other 3 are not typically used. Cosecant, secant, and cotangent, they are extensions of the main 3, and so we stick primarily to the inverses of the originals. So, one more time, the idea of these inverses is they will take in the ratio and put out the angle. To show this very plainly, I'm going to actually do one we've actually done before. So, first of all, for your problems today, as a reminder, because many of them will use calculators, make sure you check your mode. Some of your homework problems will be in degrees, some will be in radians, some will specify to give both answers. So make sure you're checking your work, make sure you're checking the problems to get the correct solutions, because you can actually take either one of these problems. For a second, I'm going to switch to degrees. So, in this case, I'm going to use one we actually have on the unit circle. For today, we're going to stick primarily to calculator-based inverses. Tomorrow, we'll extend this idea into using the unit circle as well. It's not as far as you think it's going to be. It's actually pretty straightforward, and it actually makes it nice to get you onto the calculator for it. Here we go. Example, sine of 30 degrees. So if you remember your unit circle, you should already know what that solution is. Sine of 30 degrees in this case, square root over 2, and a decimal point 866. So that means that what I do is, for the sine function, I plug in the angle, and it outputs the correct solution, 1/2 in this case. What the inverse should do is the opposite of that process. So what I can do now is I can tell it, hey, the answer is 1/2. Tell me what the angle was. Again, it's always the inverse of that process. So if I think about it in terms of the words, it makes a lot more sense. Before I plugged in the angle, got the ratio. Now I'm plugging in the ratio to tell me what the angle is supposed to be. So what's my angle? 30. Now, we discussed before with unit circle how the unit circle generates multiple solutions. The calculator will only find the main one. That's why we'll use the unit circle for a lot of problems, because it can tell you more than just the one solution. Yes. But for now, note, again, this relationship. The original function, you plug in the angle, 30. It'll come out with the ratio, 0.5. The inverse, you plug in the ratio, 0.5, and it will tell you what the angle was, 30. It always works this way. There's no hard problems tonight, and for what you have for this week, there will be some that are just real simple calculator problems. They'll say, hey, evaluate these inverses. Speaking of which, let's do a couple easy ones. Calculator out, please. We're going to evaluate a few of these. Now, for these problems, I want you to tell me both solutions. I want you to do it once for radians and once for degrees. Here we go. Tell me, evaluate. What is sine inverse of 7 over 12? Cosine inverse of 5 over 8? And tangent inverse of 3. So these are nice, simple calculation problems. But keep in mind, as you do these problems with the calculator itself, what are we actually doing? What we're doing is we're taking the ratio from some triangle. In this case, for the sine function, as a reminder, this means my opposite side is 7, my hypotenuse side is 12. Because remember, it's the ratio that we're now plugging in. For the cosine, this means my adjacent is 5, my hypotenuse is 8. For the tangent function, this means that opposite over adjacent simplifies to 3. What this will do is this will tell me, hey, this represents some angle of the triangle. To put this in very plain perspective, we are now talking about a picture with the following properties. The opposite side is 7. The adjacent, or the hypotenuse, is 12. Here in black is what I've asked you to do. There in blue is the actual problem itself. We have taken the sides opposite of 7, hypotenuse of 12, and we're using that to determine what the angle is, because that's what an inverse relationship does. The second one, same process. The adjacent is 5. The hypotenuse is 8. We're trying to find x. Before you ask, yes, we could have this distorted. It could be flipped. It could be slid to the side. This could be reduced, so it's not actually 5 over 8. It could be like 10 over 16, where it reduces to 5 over 8. But again, notice that we are taking the ratio that we have from the triangle to determine what the angle is instead. So the tangent one, a little weirder. But remember, any number can be represented as over 1. So 3 over 1 would make sense here. So, another way to ask this exact same question would be, hey, what is the angle if sine inverse of 7 over 12? So, let's find both here. Let's start with the degree. So for the first problem, what is sine inverse of 7 over 12 in terms of the degree? What do we get? No one found the degree yet?
35.68.
35.68. For the degree, 2 decimals, beautiful. Some problems will say round to the nearest one. In this case, the answer would be 36. Some will say go to 1 decimal, some will say to go to 2. Read your instructions. For the radian, what's the radian version of that answer? I prefer the fraction. But if all you have is a decimal, give me a decimal.
0.62.
0.62. Now for the radian, it's common to go to either 3 or 4 decimals.
3.
Give me 3. 0.6. Give me 3. Okay. So you have the degree version, which means that in this picture, this ratio, 7/12, is created by the angle of 35.68 degrees. That's the big idea of the inverse. We tell it the ratio, and it tells us what the angle should be. Again, that's the opposite effect of what the traditional sine function does, where we plug in the angle and find out the ratio afterwards. Cosine inverse of 5/8. What is the degree? 51.31 degrees. What is the radian?
0.895.
0.895 radians. Beautiful. So what this means is an angle of 0.895 radians produces 5/8 as a ratio. Again, they're interconnected. But the inverse just does the opposite order. Radians, RID, red. All right, last one. Tangent of 3/1, or 3. The radian value? What did I go in reverse? Sorry, degree value first?
71.56.
31.56 degrees. Okay, what about the radian value?
1.249.
Radians, RAD. So again, an angle of 71.56 produces a ratio of 3 for tangent. An angle of 1.249 radians produces a ratio of 3 for tangent. It's designed to work backwards, always. Now these are ones that you cannot possibly do by hand. There is no way these are not nice values. Most of your homework problems are actually ones that we will learn tomorrow you can do by hand, because they match with things that are on the unit circle. Now, this might start to feel like a little bit of a flashback to geometry. Those of you who may not have blocked it out just yet. So, the common use for these inverse functions is to find missing angles. So, I've given you evaluate problems. Let's look at some basic geometry ones. Here we go. One more time, a couple of examples. Find the missing angle, x. Let's see, find the missing angle, x. So, as some of you guys are already discussing, unlike with the evaluate problems where you're just asked to solve, these ones have an extra added layer of complexity because you may not necessarily know right off the bat which trig ratio you're supposed to use. That is why it's important when you're looking at a problem like this to take the time to find out which ratio is which and identify your components from last semester, opposite, adjacent, and hypotenuse. Yeah. I'm going to find... Alright, for all of these, let's do the degree version this time. Instead of finding both, let's just do the degree version. So, to do these kinds of problems, one of the first and primary key steps is to determine which of the ratios you have in the problem. So, remember, sine is only applying if we have opposite and hypotenuse. Cosine only applies if we have adjacent. Hypotenuse tangent applies only when we have opposite over adjacent. So in these particular problems, there is one ratio which is usable from the beginning. So this first one up here, top left-hand corner. Which ratio is the right one? Sine. So in this case, the 4 represents our opposite side. The 5 represents our hypotenuse. Those two are common to sine, which means to find the missing angle, what I want to do is first of all recognize I have the ratio, I want the angle, which means I need to use an inverse. I have the ratio, I want the angle, I should use an inverse. Last semester we spent a significant amount of time looking at the opposite, where I'm given the angle and want to use it for something. That's where we use sine, cosine, and tangent. We use the inverses when we want to find the angle itself in these kinds of problems. So let's plug them in. So in this case, my function would be sine inverse of the ratio. Make sure to do the ratio correctly, or otherwise it might not pop a solution. In this case, my opposite over hypotenuse, so 4 over 5. This should tell me the angle for this problem. Make sure it's in degrees for these ones. What is the solution to this first one? In other words, what is the angle that is missing in that first picture?
53.13.
53.13 degrees. So this angle, that missing angle x, is 53.13 degrees. So again, the common first approach is identify the sides you have, so you can identify which trig function will work, and then which version of the trig function do you want to use. Because both options are now available to you. I think every problem you have in your homework deals with inverses, because this is the inverse section. But as we go farther along, we may start mixing. Sometimes you need to use the sine, sometimes you want to use sine inverse. It depends on what you have in the problem. So you want to make sure you do the right thing. Top right, I have sides 8.4 and 7. Which trig function are we going to use?
Cosine.
Why cosine?
Because it's theta adjacent.
Okay, which one is adjacent?
7.
Which one's the hypotenuse?
8.4.
Yep. So you are correct. We're going to use cosine, but we're specifically going to use cosine inverse. Let's set it up. Go with an inverse. So to use the inverse, what I want to do is I want to plug in the ratio 7, 8.4, and this should output the angle itself. When I plug it in, Julie, what we get?
33.55.
33.55. That's awfully duplicated. Degrees. Don't forget the degree symbol. All right, last one. 6.3, 7.1. Which trig function are we going to use? Now I have to start getting picky. We ain't going to use tangent. Don't lie to me. We ain't using tangent. Some of you don't realize the trick. We are not going to use tangent.
Inverse.
We use tangent inverse. That's right, Remy.
I was like, well, there's no way.
They are two separate functions. This would be like saying, I want to use a square when you meant to say I want to use square root. They're two different things. They act differently, they do different things. One inputs one thing, outputs something completely different. I know what you're going for. It's the gotcha. But I'm going to start being specific. Because if you say tangent, you could mean tangent or you could mean tangent inverse. I'm confused. No. All right, let's plug in. So again, to use tangent inverse, I have to, again, plug in the ratio so I can find out what the angle is. My ratio in this case, I want to put the right pieces together. So 7.1 is my opposite. 6.3 is my adjacent. So I set it up. Opposite, 7.1 over adjacent, 6.3. And then I find my angle value.
48.41.
48.41? That goes. Degrees. Now, for some of you, you've already got this. You remember your challenge really well. So let me pose a challenge to you. One more example. This time, you don't get a choice. You have to use the trig function I tell you. Here we go. I want you to find the missing angle for this picture with the following pieces. And I want you to use tangent inverse. You do not have a choice now.
Okay.
Prove to me it's possible. Because I claim it is. What's the obvious one I should use? Sine. I should use sine inverse. But I tell you, I want you to do it with tangent. Because I can. I'm a teacher. Sorry. Do it with tangent. What's the problem with doing it with tangent? I need to have that missing side. Brian's already on the right track. What are you talking about, Brian? Yeah. It's Pythagorean theorem. Every problem that we have like this in our homework, you can actually use any of the trig functions to solve them. It's just some of them may end up being a lot more work than the more obvious one. The best answer on this problem would be to use sine inverse and then move on with your life. Could I do it with tangent? Yes. Just once, I'm going to make you use tangent. On your homework, I don't force you to do anything. Just know it's possible, but you have to do more work. So, let's go ahead and find that missing side using Pythagorean theorem. Pythagorean theorem, as a reminder, states a squared plus b squared equals c squared. Or, as we talked about earlier this year, o squared plus a squared equals h squared. Okay? So I've got a question mark, which I could label with a variable if I wanted to. I just can't use x. I've already got that problem. I got 7 and I got 6. Where do those numbers go in my Pythagorean theorem? So what? I've got 7, I've got 6, I've got a question mark. Where do those go in Pythagorean theorem?
6 squared plus b squared equals 7.
Okay, I hope that's clear. That's a 6 next b. 6 squared plus b squared equals 7 squared. The 7 is the hypotenuse, so it has to be our c value. The a and the b are 6 and b. So we solve. 36 plus b squared equals 49. We subtract from both sides, getting b squared by itself. B squared is 13. As a reminder from last semester, how do we find out what b is? We got b squared equals 13. Square root both sides. What's my b value? But because we're dealing with trig, we assume we're going to use the positive solution. So, square root of 13, I have not used a calculator yet, so that's good. Which means this missing side is the square root of 13. Now I can do tangent inverse, because I have the ratio I need. I have the opposite and I have the adjacent. I could do tangent. Let's do tangent inverse. What's going to go into my fraction here? 6 over square root of 13. But Douglas, you told us to simplify stuff like that last semester. Not when you're just going to plug it into a calculator. Just plug it in, okay? So, tangent inverse of 6 over 13, sorry, 6 over square root 13. What do we get as our angle in degrees, please?
58.99.
58.99. Now, why on earth would I demand you do it with tangent? Because I'm going to do it again with what we should have started with. In theory, since it's the same angle, if I was to start with using the sine function, I should get the exact same angle. 58.99. I want you to know these all fit together. So if I instead had done this problem like we started with sine, and done sine inverse, first thing I want to point out here, you'll use a different fraction because sine uses a different ratio. Sine uses opposite hypotenuse. So what we should have used was 6 over 7. So when I type that in and do sine inverse of 6 over 7, I actually do get the exact same solution, as long as you use the exact values. If you type in square root of 13 as the decimal version, which is like 3.7 something, you will get an answer that is close to the same. If you use square root of 13, you will get the exact same solution, because they should work that way, right? It's an angle. It's not changing just because we use a different ratio, it's still the angle. So this is the inverse. They're designed to fit together. We spent a lot of time last semester looking at how these pieces fit together to find missing sides. Inverses are designed to do the opposite. They find the angle. But again, you have to know how the originals work to get these to work. Now, to re-clarify. Today we spent primarily looking at the calculated version of these problems. Tomorrow, we'll do them without a calculator. It will require the use of two things: a unit circle or Pythagorean theorem for a lot of it. So, if you ask me what your homework assignment is for tonight, I will not post your homework tonight. I will post it tomorrow. Your homework tonight is look at the unit circle again. It's been a few months. Look at it again. Look at it twice. 3 times. Look at the degree and the radian. Find a video if you need to. Unit circles. We will look at it again tomorrow. It will be impossible to do anything tomorrow if you have no idea what half unit circle is. It will be impossible. If you need a cheat sheet for tomorrow, I'm not going to be looking at your desk, but you best relearn it quickly. If you need to print yourself off one, I will not judge you, but learn it again and quickly. But tomorrow, I will not allow the use of a calculator for any of it. No calculators allowed tomorrow. So make sure if you don't have that unit circle memorized, have something.
It was good cereal tomorrow.
All right.